Today we're going to talk about Poisson processes and the Poisson distribution, if I can spell it correctly. And our learning objectives for today are: first, we're going to define a Poisson process, Poisson, and its distribution. Which are related to number of events occurring within a period of time or space with a mean occurrence rate. We'll dig into that a little bit more. We're going to describe the time between occurrences, two events, that follow a Poisson process as an exponential distribution, which we'll probably get to next lecture. And that's related to the geometric distribution, because the geometric distribution says how many events or trials between neighboring successes or events. How many trials does it take to get between successive heads flips, for example, of a coin? And so if the Poisson process is the number of events occurring within a period of time, that's very similar to a trial, essentially. So the exponential distribution is the time between events. The geometric distribution is the number of trials in between events. An important distinction, but it is very much related to the geometric distribution. And then finally, we're going to compare Poisson processes with Bernoulli trials. The Poisson distribution with the binomial distribution. And the geometric distribution, well, I'll keep it this way, the exponential distribution and that's that table that I introduced that we'll talk about in a second. They're all kind of related, but this kind of series, Bernoulli, binomial, geometric, are based on discrete variables or trials. And in a Poisson exponential, we won't talk about the gamma distribution, but these are based on continuous random variables, time or space. So let's get into a little bit more of what the actual Poisson process is and its definition. So we'll kind of first define it as describing the probability of n events occurring over time or space, but we'll just talk about time right now, t. So space could be x, right? You're going to kind of think about the number of events that occur over a length of a road or a pipeline or something like that. Kind of think about one-dimensional space as easiest way. And so for a Poisson process, we're going to define it just like we define Bernoulli trials. The events can occur randomly. At any points. In time or space. So it's kind of like evenly distributed, right? It could happen anywhere. There's not like a clustering. The occurrence of an event in time or space is independent of other non-overlapping events is independent of other non-overlapping time and space intervals. So what happens in this interval, we'll just say delta t is independent of what happens in this other interval, right? There's not this like communication across intervals. And what this means is we have no what's called serial correlation. Or spatial correlation. For these distributions to apply. Serial just means across time, and then spatial, of course, is spatial correlation. So do we have clustering essentially in space and time? So this is essentially no, it's random. And then we say the probability of occurrence of the event in time interval delta t is proportional to delta t. And is equal to some rate term, which we'll call nu delta t. So nu is going to be this term that we're going to define as the mean occurrence rate. So you can define that as like number per time, right? Or number per space. So it's a nu, and then delta t. Yeah, it looks like a V, but it's not. All right, and then the last thing I'll say is the probability of occurrence of two or more events within this time interval delta t is negligible. For small delta t. So we're defining delta t as small enough, and essentially we're going to be taking a limit, right? So as delta t goes to 0, we end up with the Poisson distribution and the exponential distribution, because we're going from delta t, you could think of as a discrete chunk of time, but then we're going to take it to its limit infinitesimally small, and then we get a continuous variable. So it's essentially what, deriving the derivative, for example, right? As delta x goes to 0, we get the definition of a derivative. So we'll write out the Poisson distribution. We're not going to derive it, but if you are interested in the derivation, you can see Appendix C for the derivation. I think I'll scan it and post it on Canvas too, just so you have it. It's very interesting. But what we're going to define is we'll define our random variable xt, which is equal to the number of occurrences of event x over time t. Could also be space x or some other variable we're going to define. And we'll write out the distribution this way. So the probability that our random variable is equal to some value x, the number of times over our time period, over a period of time, is equal to that mean rate parameter times the time interval that we're interested in, all over x radical, and then this is to the x, times e to the negative nu t. So nu again is the mean rate over space and time. So this is our Poisson distribution. And you can do this, you can do the calculus to prove it to yourself, but we'll just say the expected value of x sub t is equal to the mean rate times the time. So if I have a mean rate of 10 times per minute, and I want to say what is the expected value of number of occurrences over an hour, then I would just say 10 times per minute times 60 minutes. So 600, I would expect to see this thing occur 600 times in an hour. So very, very simple there. And then the variance of x sub t is equal to also nu t. And then of course the standard deviation is going to be the square root of that. So the variance increases with the time period that you're interested in. So that's the Poisson distribution, and it's very, very similar to the Bernoulli sequence and binomial distribution. So we'll just talk about it briefly. So we know that Bernoulli trials are discrete events. We'll just say discrete events. Discrete random variables, yes or no, does the success happen or not? And we can think of it as counts, number of successes over n trials. And that ultimately gets us to the binomial distribution, right? Number of successes over n trials. Poisson works the same really as the Bernoulli, right? So Poisson process, it's not a trial, it's a process. That's kind of the way we define it. Instead of trials, it represents time intervals or space intervals. And we know that mathematically that the Bernoulli distribution approaches the Poisson distribution. For an approaching affinity. So as we keep increasing our Bernoulli trials, and maybe I should be saying binomial, but as we keep increasing our Bernoulli trials out and out and out, then we end up with, in the limits, the Poisson distribution. So I'm going to give you just an example of a Poisson process, and then I want you to think of some other examples. So you've already done this before, and we could think of it in a number of different ways, but we can think of it as a Poisson process. So we could think of the number of cars passing through a traffic light. Cycle, which has, we'll say, 90 seconds. And we could think of this from the kind of Bernoulli binomial perspective and say one light cycle, delta t is equal to 90 seconds. That is one trial, right? That would be our geometric formulation of it. But we know that, okay, so we have 90 seconds and 5 cars pass through the light, and then the next time 4 cars pass through the light, and the next time 6 cars pass through the light. We can ultimately estimate an average rate, cars per second, right? So we could say nu is equal to cars per second. And then we can take that delta t and make it go to 0. And so now we have this continuous distribution. Instead of 90-second chunks in a trial, now we have a rate of number of cars per second. And now we have this continuous variable. And we can ask different questions of what's the probability that xt, or we'll just say number of cars, is equal to 10 over so many seconds in this case. So I'll say over 60 seconds. If we want to shorten the light cycle or something like that. So the distribution, if we go back up here, we can see that it has 2 parameters. It's got this rate parameter, which is something that we determine from our data or from theory. And then we have to specify the time interval, t, that we're interested in, the time period or time frame that we're interested in. And then we can calculate the probability that we'll see this many cars. So why don't you all take a minute to think about other examples of Poisson processes or things that could be turned into a Poisson process. Jaden, what do you think?
You could do something like how many cases of a disease per so much time. It could be, I guess, like days or a week or whatever.
Okay, so disease, you guys, disease counts over days or weeks. And the idea would be, okay, like right now, and why don't you guys talk amongst yourselves? Right now we have so many cases per week of COVID, and if we kind of use that as our mean rate, we could say what's the probability that we have 100 cases in the next 2 weeks or something like that. You could like apply that out.
That makes sense.
Or, heart attacks. If you're, a person, let's just say, male over 65, and we know the mean heart attack rate for that demographic, then what do we expect? How many heart attacks do we expect to happen over this month or next year or something like that?
That makes sense.
What did you guys come up with an example? Okay, viewers on a streaming service. So what is the, what's the rate parameter? Yeah. Okay, so we'd say new is views per day. And then what's the question you could ask of this? Okay. And so you could break that up. You could break that up by age or I don't know, geography. Yeah, just kind of like economic status. And then you could say, okay, what's the kind of views? How many views would we expect over a certain time period based on those? Yeah, great. And then did you hear our example of disease counts? Like how many people get a certain disease or have a certain health condition happen over time? So new in this case would be number of cases per week or day. And then you could say X, T would be the number of cases over a certain month or a year, something like that. And if we want to do the spatial example, we'll have some actual examples of that on problems and stuff like that, but it could be number of potholes per mile in a road. Okay, so we go out and do a survey, we collect the data, and then we have, maybe we say, so this is a space example. We say we have a crew that can repair 10 potholes in an hour, or maybe that's a big number, I don't know. So we can say our crew can repair, this would be our rate parameter, our crew can repair, let's say five potholes per hour. So you could then use the Poisson process and Poisson distribution to figure out, well, if I've got 10 miles of roads that I need to investigate, how many potholes do I expect over that 10 miles? And then, I mean, obviously that's an easy thing to calculate. Well, if I have 10 miles of road, then I expect to have 5 times the rate, right? So the expected value of X would be just new times our mileage. But if my crew, you could ask kind of more sophisticated questions and say, if they can only repair 5 potholes per mile, what's the probability that I only have 5 potholes per mile, or sorry, per hour? And then you could start figuring out the probability that they would be able to finish their job in a certain amount of time or something like that. So you could then run some, we have a 95% chance that there are less than 10 potholes or something like that, right? So there's some more sophisticated questions you could do. What's that?
Estimating road projects.
Oh, I'm sure. And then multiply it by 3. Well, no, they're wrong because they don't do it from a probabilistic standpoint.
Okay.
Yeah. So if you did this more probability kind of thing, then maybe you'd have better success. So, all right, we'll do a couple. I think we have time for a couple examples here. Some actual problems to do. Okay, so example 1 is going to be earthquakes. And I'll just take this out real quick. Okay, so over the last 50 years, Southern California has experienced 2, we'll just call them large earthquakes. And that definition of large in this example, magnitude is greater than or equal to 6. Find the probability of an earthquake of similar magnitude occurring in the next 15 years. So we're going to do it first as a Poisson distribution, and then we'll do it from the binomial perspective. So what we're asking here is the probability that we're going to have one occurrence over 15 years that is at least 1, so greater than or equal to 1. And I didn't define the cumulative distribution function for this, but we can write this as we can write this using the probability density function. And so if we're thinking of greater than or equal to 1, what's that equal to? If we're just going to be based this off the PDF where we use equal signs inside this rather than inequalities. Yep, so this is going to be 1 minus probability that over 15 years we have no earthquakes. Now, before we get into this, then we need this rate parameter nu. And so what's that equal to? Based on the information we have, what's our rate? Yeah, 2 over 50. Not a huge data set, but it's something to work with. So if we assume that it's a kind of constant rate over time, which may or may not be true with earthquakes, I don't know, then we get a rate of 0.04 per year. So that's our rate parameter. And then we can plug this into the PDF for the Poisson distribution, which is going to be 1 minus, so the PDF is in here, and that's nu t to the x all over x radical e to the negative nu t. Plug our values in. And then we can go and calculate that. And zero radical is just 1. So we end up with 0.45. So 45% chance of having an earthquake, a large earthquake over the next 15 years. But the formulation of this statement is very similar to the binomial distribution. And so we can also do this if we treat each year as a trial binomial. But we're going to get a slightly different answer. So for binomial distribution, we need to know n and p. So it's the probability that x is equal to x given n and p. That's our binomial distribution. So in this case, what is n and what is p? So 15 years, we're treating each year as a trial, and then p, probability that we have an earthquake in a given year, 0.04. So that's essentially, we're saying p is our rate term. That's the kind of correlation there, or relationship between these two. So that we'll write it out again. So this is probably that x is greater than or equal to 1 is equal to 1 minus the probability that x is equal to 0. And then we can do our binomial distribution. So that's going to be 1 minus, and here's the binomial, which is 15, choose 0, 0.04 to the 0, and then 1 minus 0.04 to the 15. That's going to be n minus x. And so if we do that problem, we end up with 0.046, or sorry, 0.46. Not far off, but not the exact same thing, right? So essentially this Bernoulli distribution would be an approximation of a Poisson process, but the two converge as you as n increases and as our kind of trial interval decreases. Let's do one more. And this will be a space example. Not an outer space example, although I should have those. So we have a pipeline that transports crude oil to a refinery over a length of 100 kilometers. Past inspections of the pipeline indicate that an average of 15 corrosion spots occur along the length of the pipeline. That require repair. So the question then is, find the probability that there will be 10 locations requiring repair in the next inspection. So kind of similar to that pothole repair example, what resources do we need to bring to this? How many inspectors and how many supplies and materials and that sort of thing? So it's a little bit more nuanced than just saying, well, on average it's 15. You could start asking some more sophisticated questions of this. So this is the probability that X over 100 kilometers is equal to 10. And we'll calculate our rate. So what is the rate here? In this case, it's number over length. So 15 over 100 kilometers, 0.15. And then we plug this into our equation, we get nu t to the x over x radical e to the negative nu t. And then we plug that into our calculator and we get 0.049. So we have about a 5% chance that we'll have 10 corrosion spots on the next inspection. Then you can get into inequalities and the cumulative distribution function and ask more sophisticated